So we're back. And one last of the practice problems that I want to work. And this was a study of allele frequencies for a gene that codes for an enzyme called malate dehydrogenase in a small freshwater crustacean called the water flea Daphnia, which you might have seen in earlier classes. It's a pretty popular experimental critter for undergrad labs. In 1400, the non-majors biology course, we make them do a lab where we study the effects of different alcohol concentrations on Daphnia's heart rate. Because the crustacean is transparent and it's pretty easy to see the heartbeat. Anyway, there's 3 alleles of this gene, and they're abbreviated S, M, and F. By the way, that's short for slow, medium, and fast. And they're called that because, again, we're detecting these alleles with electrophoresis. And slow, medium, and fast refers to the rate at which electrophoresis bands migrate through the gel, right? The S band takes the longest to move away from the well, and it's going to be closest to the well. And the F is going to move the farthest from the well. Okay, so there's the data that's, since the guy's British, I assume his name is Hebert, although in South Louisiana, he would be Hebert, because, you know, French. But there's his data, and we get to calculate the allele frequencies. You know what? I'm going to keep the room lights on just so I can see what I'm doing when I'm typing, because mistyping things because the keyboard is shrouded in darkness is getting kind of old. So let's go ahead and share the whiteboard and erase all of that. Got a nice clean whiteboard there. And I will really quickly, and now that I can see what I'm doing, this shouldn't take too long, copy down the data. I want a darker color. So we have 3 individuals with genotype SS and 8 individuals with the genotype SM. S&M, make that joke, and 3 with the genotype SF, and 19 with the genotype SF, sorry, and 15 with the genotype MM, and 37 individuals that are MFs, and 32 that are FFs, for a total 114. Okay, first thing we got to do is calculate the allele frequencies. And this is pretty easy because if we have 114 individuals, we have 228 alleles, right? Yes? So let's just let P be the frequency of the S allele. And how do we calculate that? Well, we've got 228 alleles. How many of them are S alleles? Well, the SS, we have 3 individuals that have 2 S alleles, right? So that's 3 times 2. And we have 8 individuals that are SM, and they have 1 of each allele. 8 plus 1, 8 times 1. And we have 19 individuals that are SF. Right? So that's our total number of S alleles, right? 3 have 2, and 8 are the SMs, and they have 1, and 19 are the SFs, and they have 1. Make this a little bit bigger now and give myself a little more room. There, put that all on one line. And we divide that all by 228. Okay, we'll let Q be the frequency of the M allele. And that equals, let's see, we have 15 individuals that are homozygous for it. So that's 15 times 2. And we have 8 individuals that are SM. So that's 8 individuals that have 1, right? But we also have the MFs down here. And there's 37 of those. And they have 1. And then we divide the whole thing by 228. And then for the frequency, we'll let R be the frequency of the F allele. And that is equal to, we have 32 individuals who have 2 F alleles. And then we have 19 SF individuals who have 1. And we also have 37 MFs who also have 1. We divide that by 228. Anybody want to plug and chug the numbers? Does everybody see how I'm getting this? Please tell me that when you get the exam, you're going to be able to do this yourself. Okay. Again, I see people just try to memorize formulas, and sometimes they just completely crash and burn because they don't know what numbers to plug into the formulas. I'm going to try to de-emphasize formulas a little bit, but the reason we're working these is I want to show you, give you the rationale behind these things that we've learned. Okay. What's that? Equals 0.145. All right. Okay, Q is going to be 0.329. Then R is going to be, what's that? 0.526. Okay, quick check. Do these add up to 1? Let's see, 5, 9, and 6, 20, carry the 2. 4, 6, 8, carry the 2, that's 10, carry the 1, 3, 5, 1, and add the 1. Yes, the sum of those is 1, so we have done the math right. And again, I've said this before, and maybe it's too obvious to mention, but I've seen people blow up on this. If you add these up and you get 0.999999, all that is rounding error. You still did the math right. Okay, I've seen people add up their numbers and get 0.99999 and conclude the population's not in Hardy-Weinberg equilibrium. No, it just means that you have a little bit of round-off error. And the reason why we're doing this is not to test anything. It's just to make sure we punched all the calculator buttons correctly, right? We're just checking our arithmetic as we go. Okay, so that's the first part. The second is our population in Hardy-Weinberg? Okay, well, to answer that, we can actually try to set up We can even do this as a table where we're comparing observed and expected. Okay, what's our observed frequency of big S, big S? Well, it's 3 out of 114, right? We got 114 Daphnias, and 3 of them have the SS genotype. Our expected is going to be p squared, and that's equal to 0.145 times 0.145. Okay, so somebody go ahead and plug and shove those. What's 3 divided by 114?
0.026.
0.026. All right, our expected is 0.145 times 0.145. Sorry? 0.021. Okay, so far, so good. Frequency of SM, the observed, is 8 divided by 114, which is whatever it is. And our expected is going to be 2PQ, which is 2 times 0.145 times 329. All right, do we know what those are yet? Calculator people.
Observed is 0.070.
0.070. Okay, and our expected is 0.095. All right, 4 more to go. Frequency of the SF, our observed is 19 divided by 114. 0.166. And our expected is 2PR, which is 2 times 0.145 times 0.526. Survey says 0. What?
153.
0.153. Okay. Okay. Frequency of the MM. The observed is 15 divided by 114. 0.131. The expected is Q squared, which is 0.329 times 0.329, which is 0.108. Okay. Frequency of the MFs is 37 divided by 114, which is 324. That's the observed. The expected is going to be 2 times Q times R, which is 0.329. 2 times 0.329 times 0.526, sorry. 0.329 times 0.526. 0.346. 0.346. And frequency of the FFs, the observed is 32 over 114, which is 0.289, 281, 281. 281, what, did they split it? They must have divided it equally, I hope, if 281. Yeah. Everybody knows, right? Why is 6 afraid of 7? Because 7, 8, 9. Okay. And then R squared is going to be 0.526 squared. And that's going to be 0.2 what? 277. 0.277. Okay, right. If we wanted to check our math, then if we want just to make sure we hit all the numbers right on the calculator, we should be able to add all of those observeds, and they should add up to 1 or close enough because of round off error. I don't know that I feel like 12, 16, 18 carry the 1. We might get like 0.998 or something, but again, within round off error, we should get 1. And the expected should all add up to 1 as well. 6, 9, 8, 17. I'm not going to do it all, but if they both add up to 1, it just means that we get the right buttons on the calculator. With me there? Does observed equal expected? Again, it's pretty well in the ballpark. One of the things I am seeing is we are consistently getting a little bit fewer. No, maybe not. Maybe it's not consistent. We've got a little bit more SF heterozygotes than we'd expect, but we've got fewer SM and MF heterozygotes than we're expecting. So at first I was thinking there might be a little inbreeding going on. I'm not sure if it's statistically significant though. And if we really wanted to test this properly, we just do a chi-square test with 5 degrees of freedom. If anybody feels like doing that, you can. I usually don't make people do chi-square on exams, although you are going to do it in lab. And I think that pretty much answers the problem. Yes?
I was going to ask that actually. So if you put on this problem, would you ask us if the difference is significant just from observing? So like how much difference would be?
Yeah, I might. There's no hard and fast rule for how much difference is significant. It depends on the number of alleles. So I don't think I would ask you, is this a significant result? Because I'm not going to make you do statistical testing on the exam.
So you're not going to ask us.
So I basically wouldn't ask. Or if I did, I would try to set up a problem in which it would be stupid obvious that something weird is going on. Yeah, the problems that I give you, if I ask, will be the sort of thing where you should be able to use your intuition and not quibble about whether a difference in the 3rd decimal place is significant or not. Okay, and good grief, I've got 12:10, and it's time for me to let you folks go. Have a look at the rest of the practice problems, although again, I haven't yet talked about how to handle inbreeding or selection. We'll be doing that on Tuesday and Wednesday. Don't forget that tomorrow we'll meet here, but the first thing I want us to do is go outside, and we're going to gather some actual genetic data from a real population. Wear clothes that you don't mind getting a little bit muddy, and I want to do this early because it's going to be hot, but dress accordingly. And yeah, this will be our first formal lab exercise. And I have an alternate in case it rains, but last I looked, it was not threatening to rain. Yes. Yeah, I don't think we're gonna hit every practice problem, but I'll work representatives of practice problems where you take fitness into account and practice problems where you take inbreeding into account. So yeah, I'm not gonna work every last one, but I am gonna work enough to show you different strategies. And I will also post the answers sometime this afternoon. And again, you don't have to go out and, you don't have to work them at all. I'm not gonna grade them. But they are the kinds of things that I put on tests. So think of this as watching watching game footage. All right. You have a good day. I'll see you tomorrow. Bright-eyed and bushy-tailed, same bat time, same bat channel.